There is nothing between them. Absolutely nothing. No wire, no wave, no invisible force, no secret message. They are not communicating. And yet, if you whisper to one, the other instantly knows. Across a room, across a continent, across the galaxy. That's quantum entanglement. And if that sounds like magic, or worse, like complete nonsense, good. Your brain is working correctly. Because everything you know about how the universe works, every intuition about cause and effect, about things being separate, about what it means to be here and not there, it all shatters right here. This isn't just a weird physics trick. This is a clue that reality, at its deepest level, might be a single, interconnected thing pretending to be many separate things. And the man who saw this most clearly, who was both terrified and exhilarated by it, was Richard Feynman. He famously said nobody understands quantum mechanics. But I think he was wrong. We can understand it. We just have to be willing to let go of what we think understanding even means. Now, before we dive into this rabbit hole where space itself becomes optional, if you're the kind of person who needs to know how the universe actually works, not just the comfortable stories we tell ourselves, you need to hit that subscribe button. This is Think Beyond Physics, where we don't just describe the weirdness, we chase it to its source, and I promise you, by the end of this, you will have a framework for entanglement that will change how you see reality itself. Not an easier view, a truer one. And we're just getting started. So let's set up the problem in the clearest, most infuriating way possible. Imagine I take a single particle that has a property called spin. Think of it like a tiny, perfect coin, always spinning. But in the quantum world, this coin isn't just heads or tails, it's in a fuzzy, superposed state of both spinning up and down at the same time. It's not decided. Now, I use some magic physics to split this particle into two. Not like cutting an apple, but in a way that creates two new particles that fly apart. These two children inherit a rule from their parent. Their spins must be opposite. If one is up, the other must be down. That's the entanglement. They are matched set, a yin and yang. I put one particle in a box in front of you, here in New York. I put the other in a box, and I get on a rocket and take it to Mars. Now, you open your box in New York. You peek. At that exact moment, the coin stops spinning in a fuzzy way and chooses up. The act of you looking forced it to pick a state. It crystallized from possibility into reality. That's weird enough. But here's the impossible part. According to the rule, the particle on Mars must instantly be down. Not after a delay for a signal to travel at the speed of light. Instantly. Your act of observation here seemingly determined the state of a thing 140 million miles away, faster than light could connect them. This is the puzzle that made Einstein so uncomfortable he called it spooky action at a distance. He hated it. It seemed to violate the central rule of his relativity. Nothing, no information, no influence, can travel faster than light. It would break causality, the logical flow of time. So for decades, the comfortable story was that Einstein must be right. The particles must have had a secret plan all along, like two gloves separated at birth, one left-handed, one right-handed. You just didn't know which was which until you looked. This hidden variable idea saves our classical sanity. It says the universe is local and real. Things have properties before you measure them, and influences travel at finite speed. It feels right. But here's what nobody told you, the crack in that comfortable story that started to widen in the 1960s. What if you could ask the particles a different question? Not just are you up or down, but something more subtle. What if you could measure their spin along a different axis, like asking our spinning coin not heads or tails, but red or blue? The gloves inbox's story falls apart if you can ask for the color instead of the handedness. The math of quantum mechanics makes a specific, testable prediction for this different question, a prediction that is different from any secret plan the particles could have agreed on beforehand. This wasn't just philosophy anymore. This was an experiment waiting to happen. And before I reveal what that experiment showed, and what it means for the very fabric of between, you need to understand the man who gave us the courage to even ask the question. Because while Einstein was saying this can't be right, Richard Feynman was leaning in and saying, what if it is? What then? To understand the magnitude of what we're dealing with, we have to go back to the birth of this spookiness. It wasn't born in a lab. It was born in a thought, in a paper in 1935 penned by Einstein, along with his younger colleagues Podolsky and Rosen. Their goal wasn't to prove quantum mechanics was weird, it was to prove it was incomplete. They crafted that exact thought experiment with the two particles flying apart, and they said, look, if quantum mechanics says the distant particle's state is instantly determined by your measurement here, then either 1. Information travels faster than light, which is nonsense, or 2. The particle's properties were already set in stone before you looked. Since 1 is impossible, 2 must be true. Therefore, quantum mechanics is missing the hidden variables that describe those pre-existing properties. They called it the EPR paradox, and they intended it as a knockout blow to the weird, fuzzy interpretation of quantum theory championed by Niels Bohr. Bohr's response was essentially a philosophical shrug. He said reality isn't independent of measurement. The two particles aren't separate entities with secret plans. They are a single, indivisible quantum system until you intervene. Asking what the Mars particle is really doing before you look at the New York one is a meaningless question. There is no before. This drove the practical, pragmatic physicists of the day up the wall. It felt like mysticism. And for 30 years, that's where it stood, a philosophical stalemate between two giants. You could choose your reality, Einstein's sensible, local, clockwork universe, or Bohr's fuzzy, interconnected, measurement-dependent one. This was the world a young Richard Feynman entered. And Feynman had a unique attitude. He wasn't interested in philosophical debates about what quantum mechanics means. He was interested in what it does. His famous quote, "I think I can safely say that nobody understands quantum mechanics," wasn't a statement of surrender. It was a battle cry. It meant, stop trying to force it into your comfortable, classical pictures. Shut up, look at the math, and calculate. And his calculations worked with terrifying precision. He developed a way to see quantum particles taking every possible path between 2 points of sum over histories, and this tool predicted outcomes with unbelievable accuracy. His work implicitly took Bohr's side. The universe, and Feynman's math, wasn't a collection of definite things. It was a tapestry of probabilities and amplitudes, and asking for a single, tidy story was asking the wrong question. But the stalemate needed to break. The philosophical needed to become physical. And that's where a physicist named John Bell enters the story in the 1960s. Bell was a fan of Einstein's desire for a sensible reality. He set out to prove Einstein right by finding a way to test the EPR idea against Bohr's interpretation. He asked, if there are hidden variables, if the particles do have a secret plan, what specific, numerical limits does that place on their correlated behavior? He derived a beautiful, clean, mathematical inequality now called Bell's inequality. It said, in essence, if Einstein is right, if locality and realism hold, then the results of certain correlated measurements on our entangled pairs will never exceed a certain value. It was a ceiling for a sensible universe. And then he plugged in the predictions of standard quantum mechanics. Quantum mechanics didn't just nudge past Bell's ceiling. It blew through it like it wasn't even there. Quantum mechanics predicted stronger, more intimate correlations than any possible secret plan theory could allow. This was huge. Bell had turned a philosophical debate into an experimental recipe. You could build an apparatus, create entangled particles, ask them these tricky questions in different orientations, and get a number. That number would tell you who was right, Einstein's comforting secret handshake, or Bohr and Feynman's spooky, inseparable connection. But here's where it gets wild. Bell himself, and most of the physics community, assumed the experiments would vindicate Einstein. How could they not? The alternative was too strange. The first major tests in the early 1970s, by John Clauser and Stuart Friedman, were crude. But their results started to tilt toward the quantum, spooky side. The ceiling was cracking. Then, in the early 1980s, a French team led by Alain Aspect performed the definitive experiments. With breathtaking precision, they managed to change the measurement settings on the detectors after the entangled particles had been created and were in flight. So fast that no light speed signal could possibly communicate the change between them. It closed the last possible loophole for a hidden, local explanation. The results were unequivocal. The Bell inequality was violated. Quantum mechanics won. Einstein's sensible, local reality lost. Think about what just happened. This wasn't a discovery of a new particle or force. This was a discovery about the architecture of reality itself. The experiment said, what happens here is not independent of what happens there, even when here and there have no time to talk. The particles are not separate. They are linked in a way that transcends space. It's as if the space between them, the vast, empty, astronomical distance, is somehow irrelevant to their connection. And that's where our real journey begins. Because now we have to ask, if there's no signal, no force, no thing traveling between them, what is it that connects them? What is really between entangled particles? The answer is going to break your concept of between forever. So let's build our new understanding from the ground up. We have to start by dismantling the word between. In our everyday world, between implies separation filled with something air, distance, a medium. If A affects B, something must travel that between, a sound wave, a force carrier, a photon. Information has a commute. Entanglement laughs at this idea. It shows that at the quantum level, two things can be so profoundly correlated that the idea of them being truly separate individuals starts to break down. They are better described as two aspects of a single quantum state. Let me give you a simpler thought experiment that Feynman would have loved. Don't think of two particles. Think of $1 bill. Now, I take this dollar bill and without looking at it, I tear it in half. I put one half in an envelope and mail it to you in New York. I put the other half in another envelope and mail it to me in San Francisco. We don't open the envelopes. We travel. I go to Tokyo, you go to London. Now, in Tokyo, I finally open my envelope. I see I have half a dollar bill with, say, the serial number ending in 5B. At that instant, I know something with absolute certainty. I know that the half in your envelope in London has a serial number ending in the matching pair, 5A. I didn't send a signal. The information didn't travel. The knowledge was created in Tokyo, but it was always true about London. That feels a lot like entanglement, right? And it seems perfectly sensible. It's just a pre-existing fact. But here's the quantum twist, and this is where the dollar bill analogy fails catastrophically. In our quantum case, with our spinning particles, it's as if each half of the dollar bill, before being observed, is both 5A and 5B at the same time. It's in a superposition. It's not just that you don't know which half you have, the half itself is not either one until you look. And the moment you force your half to become 5A, my half simultaneously and instantly becomes 5B. The act of observation here didn't just reveal a pre-existing fact over there, it created the fact over there. The dollar bill halves were in a shared state of being all possible matching pairs at once, and your observation collapsed the entire, non-local possibility into one specific, global reality. This is what the aspect experiment confirmed. The particles didn't have a secret serial number. They had a shared quantum identity. Now here's where your brain might explode. If there's no signal, what is the mechanism? How does particle B know what happened to particle A? The most profound answer, and the one that aligns with Feynman's shut up and calculate approach, is this: it doesn't. The question how does it know is the wrong question. It assumes particle A and particle B are separate entities that need to communicate. They aren't. In the mathematics of quantum mechanics, they are described by a single wave function, a single mathematical object that encompasses both particles. When you measure particle A, you are not sending a message to particle B. You are performing an operation on the entire, shared wave function. You are cutting the tapestry of possibilities in a specific way, and the pattern that emerges respects the original, entangled rule. The spooky action isn't an action across space. It's a demonstration that the wave function doesn't much care about space when it comes to defining the relationships within it. Let's get numerical to ground this. The speed of light is 299,792,458 meters per second. In Aspect's experiment, the choice of measurement setting was switched so quickly that for any hidden signal to communicate between the detectors, it would have to travel about 10,000 times faster than light. No signal was detected because, according to the quantum view, there was no signal to send. The correlation is immediate because it was never established by travel in the first place. It was established at the moment of entanglement, and it exists as a global property of the system. It's like having two ends of the same stick. If you pick up one end, you don't need to send a signal to the other end to tell it it's been picked up. It's part of the same object. In a very real, mathematical sense, entangled particles are more like two ends of the same quantum stick than they are like two separate coins. So, if the connection isn't through space, what is it through? This is where we venture into the deepest waters. Some interpretations point to something beneath space. The universe may have more dimensions than the three of space and one of time we experience. In certain theories, like the holographic principle, our 3D reality is a projection of information stored on a 2D surface. Entangled particles, in this view, might be connected by shorter, deeper paths through a higher dimensional geometry, like 2 points on a sheet of paper that seem far apart, but are touching if you fold the paper through a third dimension. Others, following Feynman's own path integral approach, suggest the particles are connected by every possible history simultaneously, and the correlation emerges from a sum over all those histories, including ones where influence travels faster than light, but which cancel out for any observable signal except this perfect correlation. But to be honest, these are stories we tell to comfort our classical minds. The raw, unadorned truth from the equations is simpler and stranger. Space is not fundamental. Relatedness is. Entanglement is a more basic feature of the universe than distance. Now, hold on. I can hear the objection forming. But if this is true, you're thinking, couldn't we use it to send a message faster than light? Imagine I set up my particle here, and you have yours on Mars. I force mine to be up, and instantly yours is down. Couldn't we use that to transmit a code? One flip for dot, another for dash? This is the most crucial point to grasp, and it's why entanglement doesn't violate relativity's sacred rule that information cannot travel faster than light. Let's break down exactly why. The problem is randomness. When you and I separate with our entangled particles, we have no control over what you'll see when you open your box. You might get up or you might get down. It's a 50-50 random chance. All entanglement guarantees is that whatever random result you get, I will get the opposite. So let's try to send a message. You're on Mars, waiting for my signal from Earth. I want to send a 1. How do I do it? I need to force my particle to be up so yours becomes down. But I can't force it to be up. All I can do is measure it, and when I measure it, I randomly get up or down. If I get up, great, your particle is down. But if I measure and randomly get down, then your particle is up. I have no way to choose the outcome. From your perspective on Mars, you just measure your particle. You get a result up or down, but it's just a random string of ups and downs. You have no way of knowing if I measured mine or not. For you to decode a message, you need to compare your results with mine after the fact, via a normal, slower-than-light communication channel. Hey, at 12 hours and 1 second, I got up. What did you get? And then you see the correlation. The magic, the spooky action, only reveals itself in the comparison of the two records. No usable signal, no bit of information like a 1 or a 0, actually jumps the gap. Relativity breathes a sigh of relief, but the mystery only deepens. The universe allows a kind of connection that looks like communication, but rigidly prevents us from using it to communicate. It's as if the cosmos is saying, yes, things are connected beneath space, but I won't let you exploit it. This truth is for my eyes only. Wait, it gets even weirder. Let's talk about what this means for the nature of objects. Take an electron orbiting the nucleus of an atom. That electron is entangled with the proton in the nucleus. Their spins, their positions, are correlated in a quantum dance. In fact, take any solid object, this desk, your hand. It's made of atoms, and those atoms are bound together by electromagnetic forces, which arise from the exchange of virtual photons. But dig deeper, those interactions create a vast, seething web of entanglement between the countless particles in the object. This is why the desk is solid. The definite position and solidity of the desk is, in a sense, an emergent property of an astronomical number of quantum particles being entangled with each other. When you push on the desk, you're not pushing on separate, independent atoms. You're interacting with a single, massively entangled quantum state that resists deformation. Entanglement isn't just a weird lab trick for two particles, it might be the quantum glue that holds reality together at the macroscopic scale. The line between here and there blurs not just for our lab particles, but for everything. We are all, literally, entangled with the atoms in our environment, with the light that hits our eyes, with the air we breathe. We are walking, talking networks of quantum correlations. But we're not done yet. Let's take this to its most mind-bending conclusion with a modern thought experiment called quantum teleportation. No, not Star Trek teleportation, but something real that's done in labs. Here's the setup. You have particle A, which is in an unknown quantum state, some specific superposition of up and down that you want to teleport. You have an entangled pair, particles B and C. You give particle B to your friend on Mars, and you keep particle C here on Earth with particle A. Now, you perform a special kind of joint measurement on particle A and your particle C. This measurement entangles them in a way that destroys the original state of particle A. It's gone. But here's the miracle. Because C was entangled with B, the act of this measurement instantly projects particle B on Mars into a new state. It's not the original state of A yet, it's a scrambled version. But the result of your joint measurement, which you now send to your friend on Mars via a normal radio signal, contains the instruction manual to unscramble it. When your friend applies that instruction to particle B, it becomes an exact, perfect replica of the original state of particle A. The original A is gone. Its quantum information has been disembodied, transmitted via the spooky channel of entanglement and a little classical radio help, and reconstituted elsewhere. Think about what was teleported. Not matter. Not energy. Quantum information. The specific, fragile pattern of possibilities that defined particle A. And the crucial ingredient that made it possible was the pre-existing entanglement between B and C, that nothing that sits between them, allowing a kind of quantum channel that is useless for sending a message, but perfect for transmitting the context of a state. This has been done over distances of hundreds of kilometers via satellite. It works. And every time it works, it is a direct, physical demonstration that what we call a particle state is not a local property. It is a relational property, defined by its connections to other things in the universe. So let's recap the journey so far, because we're building toward the final reveal. We started with spooky action and found it wasn't action at all. We broke Bell's inequality and learned the universe isn't locally real. We saw that entanglement isn't a signal, but a state of shared existence. We discovered it might be the fabric of solidity itself, and we can even use it to teleport information. At every turn, the classical idea of between as empty space separating independent objects has failed. It has failed experimentally and conceptually, which leaves us with one final, terrifying, and beautiful question. If entanglement shows that between is an illusion for correlated particles, what does that say about space itself? What is space, if not the thing that separates things? So here is the big reveal, the answer to the question we started with. What is really between entangled particles? The answer is both nothing and everything. It is nothing in the sense you expect. No field, no particle, no wave, no hidden wire vibrating through a higher dimension. There is no thing in the space between them acting as a carrier. But it is everything in a deeper, more profound sense. What is between them is the quantum connection itself, a fundamental ingredient of reality that is more primitive than space. Think of space not as the stage upon which the drama of physics plays out, but as a secondary effect, a kind of emergent mirage. The primary reality is the quantum state, a vast network of correlations and amplitudes. Entanglement is a direct thread in that network. When two particles are entangled, the thread is taut, the correlation is maximal, and from our limited, classical perspective, stuck inside this thing we call space, it looks like an impossible link across a void. But from the quantum perspective, the void is the illusion. The link is the reality. This is the perspective Feynman's work points us toward, even if he never said it so bluntly. His path integral method says a particle explores every possible path. For entangled particles, their possible histories are inextricably linked from the start. Their pasts and futures are computed as a single, unified sum. There is no A's history and B's history. There is only the A-B system's history. The space separating them is just a parameter in the equations, not a barrier to their connection. The universe, in this view, is not a collection of things in a container. It is a web of relationships. Space is what the web looks like when we only perceive the nodes and mistake the gaps for emptiness. Entanglement is the visible stitch that shows us the web is one continuous fabric. So why is entanglement so spooky? Because our intuition, shaped by millions of years of evolution in a middle world of separate objects and clear signals, is built on a lie. A useful lie, a necessary lie for survival, but a lie nonetheless. The truth is that separation is a derived concept. The truth is that here and there are approximations that break down at the quantum level. The truth is that the universe is fundamentally non-local. Things that seem apart to us are, in the underlying mathematics, not apart at all. The space between them isn't a connecting medium, it's a side effect of a deeper, more interconnected geometry we are only beginning to fathom. This changes everything. It means that when you look at the night sky, the vast, terrifying emptiness between stars isn't the default state of reality. It is a cold, diluted manifestation of it. The warmth, the connection, the quantum links, those are the default. The universe is not empty space dotted with rare islands of matter. It is a plenum of potential connection, and matter, and even the space between matter, are just different expressions of a single, coherent, quantum gravitational whole we don't yet fully understand. Entanglement isn't the exception. It's the rule. We are the ones living in the exception, in the classical, decovert shadow of that buzzing, connected quantum world. And every entangled pair in a lab is a tiny, brilliant tear in that shadow, a glimpse of the brighter, stranger, utterly connected reality beneath. This is the beauty of physics and the legacy of thinkers like Feynman. Not comfort, not simplicity. Truth. And truth, at the fundamental level, is always stranger than you think. It asks you to trade your cozy, separate world for a vast, interconnected, and profoundly mysterious one. It's a trade worth making. Now I want to hear from you. What part of this broke your brain the most? Was it the moment you realized there is no signal to catch? Or the idea that space itself might be the emergent illusion and entanglement the underlying reality? Drop a comment and let me know what you're still wrapping your head around. I read every single one, and the best conversations often start right there. And if this video made you see the universe not as a collection of lonely islands, but as a single, shimmering web, share it with someone who still thinks they understand what separate means. Let's blow some minds together. Next time, we're tackling an idea that makes entanglement look straightforward, the quantum measurement problem. What really happens when you look at something? Why does the quantum world blur away into our sharp, classical reality? And what if you are the reason it happens? Trust me, if you thought this was weird, you haven't seen anything yet. Until then, remember, the space between things is filled with more than nothing. It's filled with questions. And those questions are the only things that ever bring us closer to the truth.